Okay, let's unpack this.
Yeah.
Have you ever stood near a runway as a jet took off and, felt that sheer force?
Yeah.
Or maybe marveled at a rocket just defying gravity?
It's incredible.
Well, what if I told you there's this sort of invisible battlefield right there,
Mm.
where the air itself, it transforms, pushing the very limits of physics?
Mm-hmm.
We're diving deep today into something called compressible flow. This is where gases move so fast their density actually changes.
Exactly. It's not your everyday fluid dynamics like water in a pipe.
No, definitely not. It's this fascinating blend of motion and, well, thermodynamics
Yeah.
that makes our fastest technologies even possible.
It's truly a secret world hidden in the air around us. And for our deep dive today, we've pulled together some really incredible sources on compressible flow.
Right.
Our mission really is to distill the core principles, uncover the wild behavior of gases at these extreme speeds,
Yeah.
and reveal the surprising why it matters behind everything, from those roaring jet engines you mentioned, to even something as simple as, like, a balloon popping. You're going to get a shortcut to being genuinely well-informed on a topic that, well, fundamentally shapes our modern world.
Get ready for some truly counterintuitive ideas and some real aha moments, I think. These will change how you look at high-speed motion.
Yes.
We're talking about the incredible physics happening right at the edge of the sound barrier
Mm-hmm.
and beyond. So when we're thinking about something screaming through the air like a jet,
Yeah.
we can't just consider its static temperature and
Yeah.
pressure, right?
Not at high speeds, no.
This next concept, it fundamentally shifts how we think about temperature when things are moving fast. It's called stagnation properties.
Right. Think of it like this. If you could somehow instantaneously bring a moving stream of gas to a complete halt,
Okay.
adiabatically, which just means no heat leaving or entering the system.
Right, no heat exchange.
Exactly. The kinetic energy that gas had, its energy of motion, doesn't just vanish, it converts into internal energy. And we perceive that as a temperature increase, that's stagnation temperature. And it's not just theoretical, it's the actual temperature. A stationary probe, like a thermometer sticking out of the plane, would measure in that high-speed flow.
Wow, okay. So if you're flying in air that's, say, chilly 300 Kelvin,
Yep.
but your plane is moving fast, maybe 100 meters per second, the air right at the surface of the aircraft would actually heat up.
It would. To a stagnation value of, in that case, 305 Kelvin.
That's a 5 Kelvin temperature rise just from stopping the air.
Just from bringing it to rest relative to the probe, yeah.
That seems, well, crucial for aircraft designers.
Oh, absolutely crucial. It dictates everything from, like, what materials they can use to how they manage cooling systems.
Yeah.
That kinetic energy isn't negligible at all.
Okay. And you mentioned it's not just temperature.
Right. Stagnation pressure is equally vital. Think of it as a measure of the total mechanical energy available in the flow. Now, if a process like air moving through a perfectly smooth engine inlet happens without any energy loss, no friction or other messiness.
Isentropically.
Isentropically, yes. Then the stagnation temperature for an ideal gas stays constant. But, and this is key, if there are any irreversibilities, any losses like friction,
Yeah.
that valuable stagnation pressure will drop. You lose useful energy.
Okay. So this raises an important question then.
Yeah.
How fast are we actually talking about here to really see these effects become significant?
Good question. And that's where the speed of sound and the Mach number become our crucial compass.
Mach number.
Yeah. The speed of sound itself isn't just some fixed value. It depends directly on the temperature of the gas.
Okay.
For typical air conditions like sea level, it's around 343 meters per second-ish.
And the Mach number, Ma, is simply the ratio of the fluid's speed to that local speed of sound.
Exactly. So if Ma is less than 1, it's subsonic, familiar territory.
Right.
Greater than 1, it's supersonic. Much greater than 1, say 5 or more, you're hypersonic.
And right around Mach 1.
That's the tricky transonic regime. Lots of complex things happen there.
You can actually see these compressibility effects pretty clearly sometimes.
Oh, yeah. Like where?
Well, even in something really simple, like a bursting toy balloon. If you see a high-speed photo.
Ah, right. The Schlerin images.
Exactly. You see that bubble of compressed air expanding super fast, and right around it, you can actually see a faint spherical shock wave forming.
That visible circle. It's a real-world, albeit small scale, demonstration of these principles. Compressible flow in action.
Okay, so moving on. When you want to accelerate a gas, say in a jet engine or a rocket, you use a nozzle.
The standard approach.
But here's where it gets really fascinating, I think. The shape of that nozzle completely changes depending on whether you want to go subsonic or supersonic.
That's absolutely true. For subsonic flow, below Mach 1, a converging nozzle 1 where the area gets smaller does exactly what you'd expect.
Like putting your thumb over a garden hose.
Precisely. It accelerates the fluid, simple enough,
Hmm.
but there's a hard limit. A limit.
Yeah, you can only accelerate a gas up to sonic velocity Mach 1 at the narrowest point, the exit, of a simple converging nozzle.
So you can't break the sound barrier with just that shape.
Nope. You cannot go supersonic with just a narrowing tube. It chokes.
You might instinctively think, okay, just make it converge even more sharply.
You might think that, yeah.
But our sources explain that doesn't work.
Yeah.
Doing that would only move the sonic point further downstream, and it would actually decrease the total mass flow rate going through.
It's incredibly counterintuitive, isn't it?
Totally. So if you want to go supersonic, you need a different kind of beast entirely.
You need the converging-diverging nozzle, famously known as the Laval nozzle.
Well, Laval nozzle. Okay.
This ingenious design, it starts with the converging section, like before, narrows down to a minimum area called the throat.
The throat, right.
That's where the fluid absolutely must hit Mach 1 if the pressure difference is right. And then, surprisingly, it opens back up through a diverging section, an expanding section. And the fluid keeps accelerating in the expanding part. How does that work?
It does. It continues to accelerate to supersonic speeds. It's possible because as the velocity increases past Mach 1 in that diverging section, the gas density drops so rapidly that drop in density actually outweighs the increase in area, allowing the velocity to keep climbing. Area-velocity relation flips for supersonic flow.
That's amazing. And what really stands out from our sources is this idea of choked flow.
Yes, critical concept.
The mass flow rate through any nozzle for a given inlet condition actually hits a maximum value when the flow at the throat reaches Mach 1.
That's the choke point. Once the throat hits Mach 1, that's it. The nozzle is passing the maximum amount of mass it possibly can for those inlet conditions.
So even if you drop the pressure way down, further downstream, you won't get any more fluid through.
Not a bit more. The throat is the bottleneck. It's flowing at its absolute maximum capacity, governed by sonic speed.
Could you give an example?
Sure. Think about a flat tire. If a small leak develops, say 4 millimeters wide, in a tire that's pumped up pretty high, maybe 220 kPa above atmospheric pressure, that escaping airflow is almost certainly choked right at the start. The pressure inside is much higher than the critical pressure needed to reach Mach 1 at the hole.
So the air hits sonic speed immediately at the leak.
Immediately. That means the initial rate at which air escapes is fixed. It's at its maximum possible value. It doesn't matter how much lower the outside pressure is. The mass flow rate only starts to decrease later as the pressure inside the tire gradually drops over time, eventually falling below that critical choking pressure. The leak itself acts like a tiny choked nozzle.
Okay, that makes sense. So you've got this gas screaming along supersonically. What happens when it, well, slams into something? Or has to change direction abruptly?
Now you're talking about shock waves.
Right. You've probably seen pictures maybe of fighter jets with those strange cone shapes in front of their engine intakes.
Intake cones.
Or thought about the space shuttle re-entering the atmosphere and glowing red hot. Those intense boundaries, those are shocks.
Exactly. And the simplest type to understand first is a normal shock wave. Normal, meaning perpendicular, straight across the flow.
Okay, perpendicular.
What's truly fascinating here, and really important, is how dramatically the gas properties change across this very thin region.
How so?
Well, while the stagnation temperature of an ideal gas technically stays constant across the shock, because, again, no external heat is added or removed, the static temperature, the static pressure, and the density all jump up drastically, and very suddenly
they all increase.
But critically, the Mach number drops like a stone from supersonic down to subsonic.
Goes from supersonic to subsonic instantly.
Almost instantly, yes. And because it's a highly irreversible, messy process thermodynamically, you lose valuable stagnation pressure, it decreases across the shock, energy is dissipated as entropy increases.
And that sudden temperature rise you mentioned, that must be a problem.
Oh, it's a major headache for aerospace engineers, especially for re-entry. That huge temperature spike across the shock sitting off the nose of the vehicle causes significant heat transfer issues.
Right, which is why they need those special heat shields, those thermal protection systems.
Exactly that reason.
Okay, but not all shocks are normal, right? Perpendicular.
Correct. Very often they're oblique shocks. They occur at an angle to the flow.
Like when supersonic flow hits a wedge shape, or the pointed nose of a supersonic plane.
Precisely. We can analyze them by sort of breaking down the velocity into components, focusing on the part that's normal or perpendicular to the angled shock wave.
Okay. And what happens after an oblique shock? Does it always go subsonic like a normal shock?
Good question. No, it doesn't have to. Unlike normal shocks, the flow downstream of an oblique shock can actually still be supersonic.
Oh, really?
Yeah, or it could be exactly sonic, Mach 1, or it could drop to subsonic. It depends on the initial Mach number coming in and the angle of the object, the wedge angle or deflection angle.
So this raises another question then. Can you just keep increasing the angle of that wedge indefinitely and always form a nice attached oblique shock?
That's a fantastic question. And the answer is actually no, you can't.
No, why not?
Our sources, they reveal the surprising boundary. For any given incoming Mach number, there's a maximum deflection angle, a maximum wedge angle you can have before the shock can no longer stay attached to the tip.
What happens then?
It detaches, it moves upstream, and forms a strong, curved, detached bow wave standing off in front of the object. Think of the blunt nose of the space shuttle during reentry, that big curved shock.
Ah, okay. A bow wave. Like a boat in water, sort of?
Kind of analogous, yeah. And at the other extreme, for very, very small disturbances or very slight turns, you get what's called a Mach wave. It's essentially a vanishingly weak oblique shock, almost isentropic, meaning almost no energy loss.
And these Mach waves,
Yeah.
are they useful?
Very. You can actually estimate the Mach number of a supersonic aircraft just by measuring the angle these faint Mach lines make from a photograph. They did this for the shuttle, for example.
Just from the angle of the lines in a picture. That's clever.
It is. It directly relates to the Mach number.
Okay, so shocks happen when the flow is compressed or turned sharply. What about when it turns the other way, like expands?
Good point. When supersonic flow turns in an expanding direction, say around a smooth convex corner, you don't get a shock. Instead, you get something called Prandtl-Meyer expansion waves.
Expansion waves.
Yeah.
Different from shocks.
Very different. Instead of a single sudden jump, it's a continuous fan of waves, a gradual expansion, and importantly, it's almost perfectly efficient, almost isentropic.
So what happens to the flow properties?
The Mach number actually increases across these expansion waves. The flow speeds up even more.
It gets faster.
Yes. While the pressure, density, and temperature all decrease, it's the opposite of a shock in many ways.
Where might you see these?
You often see them in the exhaust plumes of rocket nozzles, especially if they are overexpanded for the atmospheric pressure they're flying in. They can create these complex diamond patterns. Sometimes pilots apparently called it a tiger tail.
Interesting. So far we've mostly talked about ideal flows.
Yeah.
Right? Often ignoring friction or heat transfer.
Yeah, largely isentropic assumptions to simplify things initially.
But in the real world, of course, heat transfer and friction are everywhere. Our deep dive wouldn't really be complete without understanding their impact.
Absolutely not. They have dramatic effects on compressible flow in real applications.
So where do we start?
Well, first, let's consider something called Rayleigh flow. This is steady flow in a constant area duct, like a pipe.
Okay.
But now we allow heat transfer, significant heating or cooling, but we assume friction is negligible for now.
Heat transfer, no friction. Where is this relevant?
Think about combustors and jet engines. You're dumping a huge amount of heat into the air, flowing through a roughly constant area chamber.
Right. Makes sense. So what happens?
What's fascinating here is how heating or cooling affects the flow speed, the Mach number. If you add heat to a subsonic flow, it remarkably accelerates it. It pushes it towards Mach 1.
Heating speeds it up. Okay, what about supersonic flow?
If you add heat to a supersonic flow, it does the opposite. It decelerates it, slowing it down, but also towards Mach 1.
Wait, so heating always pushes the Mach number towards 1, whether it's starting subsonic or supersonic?
Exactly. Mach 1 is like this limiting point for heat addition in a constant area duct.
But here's a really quirky detail I saw that kind of defies common sense.
Oh, yeah. What's that?
Well, heating generally increases temperature, right? That seems obvious.
Usually, yes.
Our sources show that for subsonic air, if the Mach number is already quite high, say between about 0.845 and 1, adding more heat can actually decrease the static temperature.
It sounds completely wrong, doesn't it?
It sounds like magic.
It's because the gas is accelerating so incredibly rapidly in that regime as it approaches Mach 1. So much of the added heat energy goes into increasing the kinetic energy
Okay.
that it actually pulls from the internal energy, dropping the static temperature slightly, even though you're adding heat overall.
Right.
Crazy, but true.
Wow.
Huh.
Okay, so that's Rayleigh flow, heat transfer. What about friction?
Right. Second case, Fanno flow. Again, steady flow in a constant area duct, but now it's adiabatic, meaning no heat transfer allowed.
Okay, no heat this time.
But now we consider significant friction. Think of flow down a long pipe where wall friction is dominant.
Got it. Long pipe, friction matters. What does friction do?
Well, friction always increases the entropy, the sort of disorder of the fluid. That's a fundamental thermodynamic thing.
Right.
And crucially, friction always decreases the stagnation pressure. You're always losing useful energy due to friction. Always.
Makes sense. And the Mach number?
Interestingly, just like heat addition in Rayleigh flow, friction in Fanno flow also pushes the Mach number towards 1.
Friction too.
Yep. It accelerates subsonic flows towards Mach 1, and it decelerates supersonic flows also towards Mach 1.
So Mach 1 is the limit again.
Mach 1 is the limit again. For both Rayleigh and Fanno flows, this means there's a maximum length of pipe you can have for Fanno flow, or a maximum amount of heat you can add for Rayleigh flow before the flow becomes choked at Mach 1 right at the exit.
You can't just keep adding heat or making the pipe longer indefinitely.
Nope. You can't expect the flow to keep accelerating or decelerating past the sonic point in the duct itself. If you try, say, by making the pipe longer than that maximum Fanno length, the flow upstream actually has to adjust. The mass flow rate through the entire pipe goes down to compensate. It's a fundamental design limitation.
So choking can happen due to area change, heat addition, or friction.
Exactly. It's a recurring theme in compressible flow.
And this seems particularly critical in things like engine inlets for supersonic aircraft.
Oh, absolutely critical. Engineers there deal with incredibly complex interactions between the shock waves needed to slow the air down and the boundary layer, that thin layer of slow-moving air right next to the surface where friction effects are concentrated.
What happens there?
Well, the strong adverse pressure gradients caused by the shocks can actually cause that boundary layer to separate from the surface, like a flow reversal near the wall.
And that's bad.
Very bad. It can drastically limit the aircraft's top speed, reduce engine performance, cause vibrations. It's still one of the most challenging problems in high-speed fluid dynamics research today, managing that shockwave boundary layer interaction.
Wow. So wrapping this up, from the silent expansion of maybe even a firecracker blast to the incredibly precise engineering of a rocket nozzle, compressible flow is this amazing field. It's where fluid dynamics really meets thermodynamics in, well, dramatic fashion.
It really is. And we've seen how even subtle changes in area or adding heat or the effects of friction can fundamentally alter how a gas behaves.
Yeah, leading to these phenomena like choking and shock waves that engineers just have to master.
And hopefully you've gained some real insights today into things like stagnation properties, how temperature changes with motion, the critical role of the Mach number as this gateway to completely different physical behavior, and how engineers cleverly use specific nozzle shapes, like the Laval nozzle, to manipulate the flow.
And also the complexities that come in from real-world messiness, like shocks, friction, heat transfer.
Definitely. The applications are truly everywhere. We mentioned tires, planes, rockets, but it pops up in industrial processes too. It's all around us.
So what stands out most to you, perhaps, from this deep dive? What's the takeaway?
For me, maybe it's the sheer counterintuitive nature of some of it. The idea that a diverging opening up section can actually make supersonic flow go faster.
Yeah, that's a good one. Or that adding heat can sometimes make a gas colder under very specific conditions.
Right. It challenges your everyday intuition about fluids.
Absolutely. So the next time you hear that roar of a jet engine, or maybe even just see a plane streaking across the sky leaving a contrail, hopefully you'll have a new appreciation for the incredible invisible physics at play. The world of compressible flow really invites you to keep asking questions, I think, and just keep exploring.